Welcome. We learned about linear algebra, matrices, and how to solve a system of linear equations. But why these things are important? Like why do we care about systems of linear equation? Actually, systems of linear equation, they are very important because many engineering system we can represent them by a system of linear equation. So we will look at two categories of like not two categories like there are many engineering applications that can be represented as a system of linear equations. We will look at two two different representations or uh, two different types of models that we can uh, use. So one is called like the lumped variable system with coupled component using linear algebra or just lumped model. So a lumped model, that's basically it's a model. Yeah. It's a black box model. So the lumped model, we call it like a black box model because it has like an input, it has an output, and we don't know what's happening inside it. And in this black box model, you can have many of them connected together. So I can have a black box model connected to another one, and they're all black box models. That's like a lumped model. We will also look at distributed system. Distributed system is not a black box model. It vary in it's like distributed in space. So here I know what's happening here, 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 what's happening here inside my system. So your system is still have input, it has an output, but inside the system, this is not a black box model. Like we know the state of the system at different spatial location. And that's why it's called distributed. And that's why one's called lumped, because it's lumped spatially, and here it is distributed spatially. So you will look at these two types of system and we will see how we can use this linear algebra to solve the system. So this video is more like critical thinking exercise. So we will do some critical thinking exercise to develop like equations for this system and like use linear algebra to solve it. So here this is an example of a lumped of a distributed system. So here for example like this is system can be represented by this differential equation, partial differential equation. It's about heat transport. It could be also like you can replace heat, for example, with hydraulic head. You can replace heat with concentration and so on and so forth. And basically, it tells you like now we have the state of we have like the state uh, we we have the state of the system at different spatial locations. So here in this cell, in this cell, like at different cell, like we have we can resolve the temperature. And this is our boundary condition. So this is type 1 boundary condition. So if this is the boundary condition, the system as a steady state is not like a changing in time. Can we find like the temperature here in this node, in this node, in this node, and in this node? Like, can we find like this temperature here? Yes or no? And the answer is yes, because we can solve this. Remember, I showed you previously how to use the Jacob method to solve this type of system. Now I will show you how to use the like matrices to solve this system. Similarly, this is a distributed system because it's distributed in space. So here you have uh, at different like this is like a different space, yeah, like it's changing in space. This would be, on the other hand, an example of a lumped model with input, output, and state. So here, this is my input. For example, I have the flow and concentration. This is my output. I know my flow, I don't know concentration, and I want to see how concentration is changing here, how concentration is changing here, how concentration changing here. In the system as a whole, this could be like a connected lake, this could be connected tanks, this could be connected reactors, and like these reactors, they have some input like concentration and flow, and then they have output. And then I want to see base, so I have some input here, I have some input here, I want to see the concentration here, here, here. So that's called lumped system because uh, it is not spatially distributed like this system. Okay, so for this one, I could come up with system of linear equation to solve it, to find like the temperature here, 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 here. For this one, I could come up with a system of linear equation like this and solve it to find concentration here, 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 here. So we will look at these two types of system in this video. Yeah. So let's start with this guy. Yeah. So with this guy, I know that here I can. This is my governing equation. So this is my mathematical model, and now I need to solve this model. Uh, what do you call this? I need to solve this model numerically. Yeah. So I need to have like a numerical solution for this model, not analytically. So to solve this model numerically, so this is my initial condition. So it's a steady state. My initial condition, I have like t node everywhere, and this is like my boundary condition. So at this boundary, for example, I have negative 20. At this boundary, I have 16. At this boundary here, I have 10. And this boundary here, I have 12. So can I solve this system numerically? Yes, you can set uh, for each of these cells. So you have like 4 cells here, and for each cell, you can basically you can say like the temperature here. What is the temperature here? So you can think like here. You can think here, here. You can just visualize it like this. Yeah, here, here, and here. So what is the temperature here? So you can assume that the temperature here, like to solve this guy, that would be the average of this one, and this one. So T1 is the average of like this temperature here, this temperature here, this temperature here, this temperature here, that would be T1. T3, for example, that would be the average of this temperature here, this temperature here at this boundary, and this temperature here, and so on and so forth. So basically, that is like for each temperature, you can formulate an equations like numerical equations that looks like this. Just take an average value. Yeah. So here, like you can say like T1, that's equal to what? So let's just do it one by one. So T1, that is equal to 10, 1, like the average value of like, because 10, like this guy here, plus negative 20, like this guy here, plus T2 plus T3. What about T2 here? So T2 here is like 1 over 4. So that is like T1, the average of T1, negative 20, like this guy here, plus 12, like this guy here, plus T4. What is T3? So T3 is like 1 over 4. So T3 is here. So that's like 10 plus T1 plus T4, like this guy here, plus 16. And what's T5? T4, like the last one, like this guy here. So that would be 1 over 4 T3, right? Here, this guy here, plus T2 plus 12 plus 16. Okay, so I have equations that looks like this. Now, can I arrange this equation and put them in a matrix form that where I can find like the inverse of this matrix and then I solve for T1, T2, T3? Yes, I can. So one way I can like just put like multiply this by 4, I can multiply this by 4, I can multiply this by 4, I can multiply this by 4. So if I did this, if I did this, if I did this, then I can like for example like simplify this equation as 4t1 minus t2 minus t3. Yeah, brings this to the other side. And then here, like what's t4? I will just keep it as 0, yeah, because there is no t4 minus 10. So similarly for this guy, I can arrange this guy as negative t1 plus, and you see the symmetry. I want to show you like how I'm putting this in symmetry. 4t2, there's no t3, so plus 0, yeah, minus t4 is equal to negative 8. Similarly, for this guy, I can arrange him as negative t1 plus 0 plus 4t3 negative t4 is equal to negative 8. And now you see how the symmetry is building. And then here, that would be 0, negative 2, t2 negative t3 plus 4, t4 is equal to this 12 plus 16, that's like 28 here. So sorry, this is not negative 8. This is 26 because 10 plus this 26. Okay, so now does this look something familiar? Yes. That is, remember, like AT is equal to B. Yeah. So these are my coefficient here, here, here. So let's write this matrix. So this matrix would be 1. So I have 4 in T1, I have negative 1 in T2, I have negative 1 in T3, and in T4 I have 0. Let's write the second one here. So that I have negative 1 in T1, I have 4 in T2, I have 0 here, and I have negative 1 here. Let's write for this guy here. And you need to put it in order. Like this is T1, T2, T3. That's why I arranged them here in order. Yeah, T1, T2, T3, T4. T1, T2, T3, T4. So negative T1. So for the third equation, that would be negative T1 plus 0 plus 4, negative 1. Yeah. And for here, like the last equation, I have 0. So you see my diagonal elements are all 0, negative 1, negative 1, and 4. Sorry, like my diagonal element are all 4. This is my diagonal element here. Are all like, see my diagonal element here? They're all 4. Yeah. So this is like my diagonal element. So here 4, negative 1, negative 1, 0, negative 1, 4, 0, negative 1, negative 1, 0, 4, negative 1, 0, negative 1, negative 1, and 4. So this is my A, my T. That would be what I just arranged it here. So you see this is T1, T2, T3, T4. So that would be like T1, T2, T3, and T4. And that's equal to what? That is equal to my right-hand side here, these guys. So my right-hand side, I have negative 10, negative 8, negative 6, and 28. Well, can I solve this guy? Yes, I know how to solve this guy because I know that T is equal to the inverse of A times B. So if I find like the inverse of this guy, like A, and I multiply it by B, so if I found like the inverse of this guy and I multiply it by B, I will get like this guy here, T. This is my T. Okay, so A times T is equal to B. Okay, so can I do this? I mean, I don't like, we will not do this analytically because that would be very difficult. So I told you, you generally do this numerically. So I will show you like how to do it with Excel, and then I will also show you how to do it with MATLAB. So with Excel, here you can just like this is you can review this matrix. So here is the steps basic. So these are the Excel functions. So M inverse, that will find an inverse of the matrix. M multiplies the product of two matrices. Transpose, that would be the transpose of a matrix. Mid, M the term like M the term that like the determinant of the matrix, here it will find like a unit, like a unit matrix. And the solution steps are as follow. You select the solution area, like where you want the solution, you enter your matrix function, and then you don't press enter. Like in Excel, like if I want like 2 plus 2, you hit enter, it will give you 4. Here you don't press enter, here you press Control Shift Enter. Let me show you an example. So this is matrix A. I want like this is the inverse of matrix A. How to find like the inverse of matrix A? So the first step, select the solution area. So I want the solution to be here. The second step, enter the matrix function. So the matrix function is inverse. So I will say like equal in like it's M in, so you have to M inverse. M inverse of what? Of like this guy. And then I close. And do I hit enter? No, I hit Control Shift Enter. So if I did this, now I found the inverse of this matrix. Can I confirm that this is the inverse of this matrix? Yes. How can I confirm? Remember, like the matrix times the inverse of the matrix will give you an identity matrix. So let me do this. So I can say like how to do it. Like you select the solution area, and then you put like here I will use a multiply function. So I will say m mult and I want to multiply like this guy, and then you put like comma times this guy here, yeah, and then do I hit enter? No, Control Shift Enter. See, I got exactly what I need. And because this is the matrix, this is the inverse of the matrix. When you multiply them, you get something like this. So here you can practice. So this is the solution. Try to like, I mean, let me do this one also. So I want to find x. So x, this is my equations. From these equations, I created this matrix because these are the coefficient. And here, this is my right hand side. And now I want to find x. What is x? X is the inverse of this guy times this guy. And I want the solution to be here. So I select the solution, I select these three cells, like this, the x, and then I come here and I hit like equal. So what do I want? I want the inverse of this guy multiplied by this guy. So I want to do like a multiplication. So what is this like? So this is m mult. What do I want to multiply? I want to multiply like the inverse of this guy. So you select here matrix inverse in matrix inverse, the inverse of what? Like of this guy. And then my second matrix, because this is multiplication, like I'm multiplying. Remember, you multiply the inverse of this guy times this guy. So that would be time this guy. That's the second one you select. Then you close and then Control Shift Enter. If I did this, then I found the solution, and that's the correct solution. Okay, so let's do my heat transport exercise. Let me delete this. Uh, here I have like this system of equation, like which I just drive for you. You can express it in this matrix form. So let me enter this matrix form here for -1, -1, and 0. Yeah. And then here -1, -1, and 0. And here 4, 0, and -1. And here 0, 4, and -1. And here -1, -1, and 4. That is my B, like the right hand side, that's like -10, -8, 26, 28, and then I want to find this guy. So what? So you select the solution area, then you come here, you enter your equation. So that's like matrix multiply. What do I want to multiply? I want to multiply like the matrix inverse in. I want to multiply like the inverse of this guy with uh, this guy. Yeah, and then Control Shift Enter. Didn't work. Then you like so I find like this guy times this guy. Oh, you have to close. Oh, see, this is the matrix inverse of this guy. I didn't close the bracket here. Time. I don't know if you can see what I'm writing here. Like I need to close this bracket times this guy. Then close the bracket and Control Shift Enter. And I got here. So what is T1? So that's T1. I got T1 -2.5, which makes sense because this is cold and this is cold. So I got like a -2.5. T2, this is cold. This is slightly hotter than this. So T2 should be larger than T1. So like if this is like a, I don't know, like windstorms that's coming from here and this is maybe the Gulf of Mexico, for example, this is the Atlantic and this is, I don't know, like Alabama or whatever, and this is a cold front that's coming from here. So in this city, for example, you expect this because this is cold and this is cold, so you expect this guy to be the coldest. So you got here -0.25. This guy would be slightly warmer because here is 12 and here is -20, so T2.25. Like this guy here uh, would be warmer than these two because this is 16 and this is 10. So like T3 is like 8.7. So you see this guy is warm. Like this guy is freezing. Guy is almost freezing, but this guy is nice, like 8.7. This guy's T4, you expect this to be the warmest because here is warm and this boundary is warm and this boundary is warm, so this guy is the warmest, and that's exactly. So now the answer, like you look at the answer, see if it makes sense or not. The answer makes perfect sense. Give him this boundary condition, I expect this to be the coldest and I expect this to be the warmest. Yeah. So this is an example. Can we do this with Python? Yes, we can do this with Python also. Let's do it with Python and see if we're gonna get the uh, same. So here I'm running Python on my machine, but I showed you in previous video how to run Python also. Like if you don't have it installed in your machine, like how you can run it not on your machine. So here, this is like in Python, for example, like uh, this is the plotting of this figure. So in this is like in So in Python, like this is like how you, oops, I shouldn't be showing you this, it doesn't matter. Uh, Let me just get rid of this guy and let me here. So in Python, like you can use this with MB array. So you put your array here. So that is like the same as we did here, like the same matrix. So you put your matrix in this form. You put like here your right hand side and then you tell him MB linear algebra solve AB. So if you did this, you got like the exact same answer, like -2.5, 2.5, 8.7, and 9.75. So basically, this is how you can solve this with Python. Yeah. Uh, let's go to the slides. I can show you like more here. So we have seen like this is your homework problem. So try to solve this homework problem. I'm here providing different boundary conditions. So basically, like you will repeat these steps and with this boundary and then try to find. Here I'm solving this problem, but here only I have like 4 cells. Here I am creating this mesh. I don't remember how many cells, but it's more or less like the same problem which is uh, actually. So this is with just 4 cells. Here I am doing this with like a number of grid points, like 50 grid points. So this was 4 grid points. Here with 50 grid points. So here you will have a system. Here you have a system of 4 linear equation. Here you will have a system of 50 linear equation. And you see, this is what I was telling you. You can solve this iteratively. So basically, like your finite difference method, you can solve it iteratively, and that's for this problem here with 4 values. This is uh, what you get. But here, see, with when you have a finer grid, like 50 by 50 grid, and with this boundary here, see, this is a cold front, and here this is like a warm area. So see something that looks like this. Okay, so you can also do it with something like this. Let me show you here. This is a real life application. So this is a model grid. This model grid has about 30 layer. This model is like solving this equation. It is solving this equation with like matrix inversion also. Like by creating a system of linear equation and doing the matrix inversion, and that's how it solves this equation. See, this model like has 50 grids, like 50 by 50 grids. This model has about almost like 400,000 grid. Yeah, but it's basically like it's so like it's based on the same principle. Yeah. So this is a distributed model. This is a distributed model with 4 cells. This is a distributed model with 50 by 50 cells, 200 and uh, 200, like 2000 cells, and this is a distributed model with 4000 cells. Why is this distributed? Because it's distributed in space, and like it's not a black box model. I know what's happening inside my system. I know the state of the system at each point that's varying in space. On the other hand, in civil engineering, we also deal with problems where we don't like use distributed model but use a lumped model. So here, for example, this example for this would be forces on a truss bridge. So I can consider each of these element as a component, as a separate component, and then I see how these components interact together with a system of linear equation. Similarly here, you see how I'm doing in time. Okay. Similarly, like we were doing good in time. Similarly here, we can treat this as similarly here we can also treat this different tanks or different lakes that are connected together, and we can treat them, we can represent this with a system of linear equation and solve the system of linear equation to find the concentration in each tank. So here this is a problem, like this is a problem statement which I'm giving to you, so you can read it. We can do mass balance by taking the flow rate. So we have like you have these are different, let's say 5 different lakes, and this is a concentration that is entering here of this nutrient or this chemical or this whatever, and so you have flow in meter cube per minute, and you have concentration in milligram per meter cube. So to get the mass flow rate in milligram per minute, you understand this, yeah? So like you have the Q, you are now expert in this, like Q, and you have C. So Q is meter cube per minute, and concentration, this is like milligram per minute. Sorry, concentration is milligram per meter cube. So you can get like the rate, they get the rate at which mass flow, because this will go with this, so that will you'll get like milligram per minute. That is like mass, so this is mass, yeah, milligram. This is mass, and per minute, Remember, like that's mass over time. And you remember we express it usually with this dot notation, like this Newton notation, if you remember from previous module. So here we have like the M, like we can just do a mass balance, like M n is equal to M out, because this is at steady state. So this system as a steady state, so there's no change in storage. So you can say like Mn is equal to M out. And basically, if we did like this mass balance, we can find like the concentration here, the concentration here, the concentration here, the concentration here, the concentration here. Because all what we know, I think something is missing here. Let me just get this number. Something is missing here. So here we have like, this is C03 is equal to 10. So this is the concentration that's entering from here. So we know like the input to our system, the concentration, we know the flow from each lake to another, and we know the outflow, and we want to find the concentration in each of these lakes. So simply like to do this, you just create like a mass balance. So you create a mass balance for each of these different components, like what's coming here, like what's entering here, like the M in is equal to M dot out. Yeah. You do it for this one, 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 you do it for this one. And guess what? Like if you did this, you will end up with a system of linear equation 5 equation. Then you can solve it, and then you find C1, C2, C3, C4. Okay, let me show you like uh, how to do this. Yeah, like how to do this for one. So let's just consider like this lake, like uh, yeah. Let us just consider like this lake here, like the lake 1 here. Okay, so let's just consider like this guy here, this lake here. So again, like the mass flow rate, that's like Q times C will give you something in milligram per minute at steady state, like Mn is equal to M out with flow cube meter per minute and concentration milligram per meter cube. So the mass balance, basically, what is the mass balance? So the mass balance here. So the mass balance here, that would be what's coming in. So that's like, so mass again, it's Q times C. So Q is 6. So you have like 6 times C, which is 5. So that's what's coming in. Like what is also coming in? What is coming in is like this guy here. So that's like C3, which is unknown, time 2. That's also coming in. So that is like 2, the flow, Q. So I write the flow first and then the concentration. So it's Q time like C3. So these are the two that are coming in, like this guy and this guy. Now what's going out? So this what's coming in is equal to what's going out. So what is going out is like the concentration of this guy, and we have like 5 units of this guy. Okay, so uh, so and we have like also 3 units of this guy. So like this guy is going out with 3 unit, like from here to lake 2 and from here to lake 5. So let's start by lake 2. So that is equal to 3C1 plus this is also going out and this is also going out. So this is 5C2. So this is at lake number 1. We can do the same for lake number 2. So lake number 2, let me delete, 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 delete. So lake number 2, what is coming in? I have this guy coming in. So I have like 3 of like C1 that are coming in. What else is coming in? That's it. So like I have 3 of this guy, that's equal to what? Like I have one of this guy is leaving to here, one of this guy is leaving to here, and one of this guy is leaving to here. So I have like one C2 plus one C2 plus one C2. Yeah. Okay. let's do for lake number 3. What do I have at lake number 3? So lake number 3, I have this guy's coming in, so uh, uh, I have 7 of like 10. What else is coming in? I have this guy, I have what plus 1 of C2, uh, like 1 of C2, that is equal to what? So so these two, so I have like this guy's coming in, this guy's coming in. And what is leaving? So I have 2 of C3 are leaving, and I have 6 of C3 are leaving. Yeah. Okay. Lake 4. uh, so I have lake 4. What do I have in lake 4? So in lake 4, I have what's coming in? I have 1 of C2. I have plus 6 of C3 plus 1 of C5. And what is leaving is like 8 of C4. Lake number 5, like the last one. So the last one, what's coming in? The last one, I have 5 of C1 plus 1 of C2, that is equal to 5 of C5 plus 1 of C5. Yeah, so that's basically my system of linear equations. So I can arrange basically this equation. So I can arrange it to like this equation, this equation, this equation, this equation. So let's start by the first one. So the first one, like you can uh, uh, I think I have a typo here. No, that's correct. Yeah, this is 5 of C1, not C2. Sorry, because this is C1 is leaving. Yeah, so that's a typo here. So if I did this, if I arranged this guy, then I will get like 8 of the C1. So I get like 8 C1, and then uh, negative like 0 of C2 or plus 0 of C2, negative 2 of C3, yeah, plus 0 of C4 plus 0 of C5 is equal to 30, yeah, something like this. And like the second guy, I have like 0 of C1 plus, no, not 0 of C1. Like here I have 3 of C1. So I have like 3 of C1 plus uh, 3 of C2 minus 0 of C3 minus 0 of C4. Sorry, plus, I mean, it doesn't matter. Plus 0 of C5, and that is equal to 0, yeah? I can like see here, I have 3 here, 3 here, everything is 0, so I can just get rid of this guy, yeah? Because I can divide everything by 3, yeah, it doesn't hurt. And then like the third equation, so you can do this for the same, like, so the third equation, what will I get? So the third equation, I will get like 0 of C1 minus C2 plus 8 of C3 plus 0 of C4 plus 0 of C5, and that's equal to 70, yeah? And the fourth equation, I got like 0 of C1 plus C2 plus 6 of C3 minus 8 of C4 plus 1 of C5, that is equal to 0. And my last equation here, I got 5 of C1 plus 1 of C2 uh, plus 0 of C3 plus 0 of C4 minus 6 of C5, that's equal to 0. Okay, so now I have something that looks like this. Does this look familiar? Yes, 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 it looks well. Here is 1, here is 1, here is 1, here is 1, here is 1. Yes, I can just like put this in a matrix form. So if I put this in a matrix form, so I got like 8, 1, 0, 0, 5. Here I got like 0. I think I have a mistake here in my second equation. That should be negative, not positive. Because like when you bring this to this side, that should be negative. Yeah. So in my second equation, I have 0, negative 1, negative 1, 1, and 1. My third term here, I have negative 2, 0, 8, 6, and 0. And then my fourth one here, I have like 0, 0, 0, negative 8, and 0. And then my last one here, I have 0, 0, 0, 1, and negative 6. Yeah? And that is what? So this is C1, C2, C1, C2, C3, C4, and C5. This is C1, C2, C3, C4, and C5. And that's equal to my right-hand side, like these guys here. So that's 30, that is 0, that is 70, that is 0, that is 0. So now I have something that looks like this. And you can do this with Excel or MATLAB or whatever. So we can do it with, let's do it with Python, for example. Like, so if you want to do this with Python, basically like what you can do here, Control C. I can, let me just here create a new Control C. Oh, I already have it. Oh, so I already have this done in Python. I don't need to do it actually. So you see here, I put like my array here, and I put my right-hand side here. Yeah, and then I do like the matrix inverse, and then that's the solution that I got. So try to do it with Excel and see if you will get the same solution. So like, see, the problem is telling you, like if you read the problem here, let's see the problem statement. So the problem statement is telling you here, if the concentration of a lake is above water quality concentration 8 milligram per meter, then this lake is not safe for recreational activity. So here we have like lake 3 and lake 4, they are above this threshold, so these are not safe for recreational activity, for example. Yeah, so that's like one conclusion yeah, you can make from this study. Yeah, so I think that is all for this lesson. And sorry, this is a very long lesson. Probably that's the longest lesson in the semester, but I kept my promise, and it is less than 2.5 hours. Because like you have 2 lectures each week, each lecture is 75 minutes, so both of them should be 2.5 hours. So everything is hopefully less than 2.5 hours. Okay, so that's all for this.